Hi, folks. Oh, I need to get the live stream running. Let's see if we can do that. Where is my live stream? Hopefully my control room. Oh, that's just going to fail. Never mind. Let me get back to... There we go. So now, can I get to the live chat? Oh, come on. Oh, there we go. Now, I hate this. They made it harder to find where the live chat is. Yes, so I found it now. Let me pop this out. You know what? This is... Let me pop this out. Okay. So now we have the ability for you guys to ask live questions. Great. And I think you all can see my screen. Oops. Yeah, I can make these things work so I can see them together. There. So let me make sure you guys can still see me. Okay, looks like you can see me. And hopefully you can hear me. There we go. Okay, somebody on live chat say, confirm that you can hear me. Say yes. Excellent. Okay, so today I like to go over a project. This is something I'm trying to make into your assignment 6, and I have delusions of grandeur about every time, and every time I get a little bit better about it. But this was from the final exam a year ago. We'll put it out as a challenge question. But I'm also am trying to evolve assignment 6 to be this at some point. Sorry, I keep on hoping it's more times to edit assignment 6. I was supposed to do it an hour ago. We'll get that. Hopefully, we'll get that out to you today, so that you guys can get started on it. And those who want to do it before the Thanksgiving break can. Okay, so first of all, let me see if there's any questions on Piazza. And if there's not, we'll go into what I plan for today. There's nothing here. Any questions from our viewers? We have 3. Nope. Okay. So here is this problem. The zombie apocalypse has happened, and now we have to go back to Morse code to communicate. And it turns out that Morse code, an international Morse code, and American Morse code are 2 different things. And so the way I want to make this problem happen eventually is that I want to teach how to actually make hidden Markov models that actually decode Morse code live. Both something where it is a set of time slots that are either active or inactive, and or a continuous time-based system. So, and then where I want to go with this problem in the future is I want to give you some unknown Morse code and have you automatically discover the individual letters and words and that sort of thing, and be able to create a system that just takes a stream of data, automatically discovers the individual parts of that data, like letters and words, and automatically create recognizers for them, all without any prior knowledge. That's where I'm going with this. However, this is the first part of it. And I said this was part of the final last year. And we're going to run through this just because I think it's fun. Okay, so zombies taking over the planets. We're trying to organize the resistance using Morse code. And what we're going to do first is international Morse code. And basically, we've taken over Georgia Tech Station REC. Yes, Georgia Tech Station is called WREK. And we have time slots, 10 time slots to encode the letters in. And the time between each letter is 10 slots, and the time between each word is 20 slots. So what we're trying to do is hook up our smartphone so that we can run this at high speed and communicate over the FM radio to the resistance movements across the nation. I should also say that we've powered up REC, so it's no longer just a 50 kilowatt station. It is now a megawatt station, so we can actually hopefully reach most of the southeast in organizing our resistance. Okay. So no pressure. Just trying to save the planet, or at least the southeast. Okay. So whenever there is basically we have two states. There's either a 0 at 1,000 hertz tone, in other words, just background noise, or we have a strong signal at 1,000 hertz tone. And so all we're doing is listening to the 1,000 hertz tone being there or not to figure out whether or not there is an on versus off state. And we're going to use that to actually convey characters. Now, this is what Morse code looks like. And, through the magic of, can I do this? Maybe. Through the magic of Hangouts, maybe what I can do is share. Okay, I'm going to make that small, so you guys can always see that. And then I'm going to put up another copy of it. That you can see at the same time. Give me a second here. I'm sitting in front of a whiteboard to do this, but I think this is going to be more efficient. Now I'll just share. Shoot. Now I can share the whole screen, potentially. Can I make this small? Yes, I can. Wonderful. I can make this small. And now what I'll do is share full screen with you, provided I don't actually cause a huge amount of problem here. Okay. So we got a little special effects going on there, but it's fine. So the first thing I want you guys to do is take a look at this hidden Markov model. Right? Now notice that its transitions are 1 and 0. Right? And so basically what I'm doing is I'm encoding a letter here. So this is the presence. This is the presence or absence of the 1,000 hertz tone. So 0 indicates that there's no 1,000 hertz tone. 1 indicates there is a 1,000 hertz tone. Right. And this could be like, you know, you also make it 500 hertz and 1,000 hertz, or something like that too, so that you actually encoding everything. But either way here, either way you want to think about it. So the question is, what is this letter? So the first thing we want to look at here is, okay, well, it's a 0 first, and in my first state, I come in here, I emit a 0, and that doesn't help us at all, because the for every letter, the first state is 0. Right? So then I come in here, and I said, and the next state is a 1. Okay, great. Well, everything is a 1 in the second slot as well. That's not particularly useful. Then I come to this state, and it's a 0 again. Okay, that's useful. That means that's either an A, a C, an E, an F, an H, an I. Oh, I guess it could be, okay, so we have to have 0, 1, 0. Okay, so I, O, P, Q, R, S, U, V, W, X, Y, Z are our options. Great. So let's see what happens next. So we get another 1. So we have 0, 1, 0, and then 1, and then 1 again, and then a 0. So we're looking at dot, dash, dot, sorry, dot, then this is a dash, and then this is a 0, and this is a 0, 0, 0, 0, 0. Okay, so 0, 1, 0, 1, 1, 0, 0, 0, 0, 0. Okay, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0. Oh, okay, so this is A, right? People see how I got that? So I've basically just taken this encoding of 10 time steps. I made a 10-step HMM that sort of encodes that. Now, if you think about this, it's not really a hidden Markov model because at every step of the way, I know which state I'm in. There's no hidden state. I mean, because I'm always transitioning left to right at every time step. So this is really a finite state machine, what we got right here. But if I think about it, I could reduce the number of states because, you know, this I can't. If I look at the emission probabilities, I have a 0 and a 1 here, and then a 0 again. So there's nothing I can combine. But these two ones together, this is equivalent of having one state with a 0.5 here and a 0.5 here. In other words, one state where I expect to stay there 2 frames. So it'd be 1 over 2. So that'd be 0.5 and 0.5. Okay. So I can reduce this to this state, this state, this state. And this is a 0.5 back to itself and a 0.5 going forward. Then let's see what we got here. We got 4 states in a row that are 0. So if I'm expecting to stay in a state 4 frames, I put a 1/4 here and a 3/4 here. And then I get rid of the rest of this. Now here's an interesting question though. If I did that, what other, is there other possible letters that this could be? And the answer is yes, actually. I haven't, since it's not specified like this anymore, this fully specifies, if I use this topology and use these outputs, I can fully specify all these 26 letters with a unique HMM for each, or Markov model for each. But when I start actually combining these things so that I have some ambiguity here, I actually have some hidden state. Well, let's see, anything with 2 dot or a dash could fit it. Well, that's not true. The first one has to be a dot because it's only 1 state long. So anything with a dot first and then something else afterwards that's just 1 dot or dash could fit. So A could fit. Let's see here. I could fit. M that can't fit. O could fit. And that's it. All right. Now, this is where things get a little bit more interesting. So what I can do is I can start and specify all these letters as a 10-state model, and then I can break them down. I can reduce them. So let's do that. So this one is an example. Oh, is that what I just did? Yes, that's what I just did. Let's do this one here. This is an example. This is a 10-state as well. And we see it's 0, 1. So it's 0. So this is 1, 1, 0, 1, 1, 0, 0, 0, 0. Okay. So 0, 1, 1, 0, 1, 1 is M. Right? And then I can reduce it down to this. This is the same M, right? Because it's 0, I have 1, 1 here, a 0 and a 1, 1 here, and then 0, 0, 0, 0, 0. But just like with A, so this is basically anything that starts out 0, has a dot or a dash, has a 0, has a dot or a dash, and has the rest of the zeros would fit. So A could fit, I could fit, M could fit, N can fit, O can fit, right? So how is it that, you guys see where I'm going with this? I'm going to actually make a model for each of the letters. But if they're ambiguous, how's this going to work? How am I going to make something that's going to automatically decode these things? Well, let's continue on. We'll talk about that in a second. Let's look at this one here. What is this one? 0. So this is going to be a dash. This is going to be a dash. Every time I see these, I know it's going to be a dash. This is going to be a dot. So basically dash dash dot. What's dash dash dot? Dash 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 dot. What am I missing here? Dash dash dot. Huh. Oh, there it is. It's G. Oh, G. It's a G. Dash dash dot. Great. So that was easy. Let's look at this one. This one's a dash, a dot, and then a dash. See, a dash, dot, dash. Dash, dot, dash. Dash, dot, dash. Dash, dot, dash. That's a K. Great. Okay, so now comes the question of, once we're kind of getting the idea of how to decode these. So now we're going to make things more interesting. We're going to assume that we're no longer actually having a machine sending out this code. It's no longer something that's going to be precise on clock time, that we can actually set something up in sync. It's going to be something that is human driven. And so we've got to deal with dots and dashes. So what we train people to do is that a dash should be 3 times the duration of a dot. And dot or dash is separated by a small white space, a small nothing, which is equivalent to the dot duration. Letters of the word are separated by a space equal to 3 dots, basically 1 dash, and words are separated by a space equal to 7 dots. Okay, so let's start with the easy thing. We need to encode this stuff. So let's talk about the next letter. So next letter we said was basically a dash. Was a space about the length of a dash. Well, in that case, we're going to put out a 0, and we expect to stay in this state for 3 time cycles, so to speak. So this would be 1/3, and this would be 2/3. Great. Next word we said was 7 zeros, basically. So that would be 1/7 here and 6/7 there. Okay, that's easy. Now, let's look at these guys. So A, here, A should be a dot. What is A? A is dot dash. Okay, so I'm going to do dot dash. So this should be a 1/3 out and a 2/3 back to myself. And then each thing is about the length of a dot. So we're going to do a 1 and a 0 here. And then a dash, which is, okay, so we had dot, white space, length of a dot. Now we have a dash, and that has to be, I said it was dot dash, right? I did it wrong. So if it's just a dot, and we just have this being 1 and 0, because we just kind of emit a 1 and immediately go to the next thing. White space is the length of a dot, so it's going to be a 1 here and a 0 here. Then this is going to be the dash, and that should be 3. We want 3 ones put out on average. So we're going to put 1/3 here and 2/3 here. Okay, so now if I actually ran this model, it would be doing dot, white space length of the dot, and then on average a dash, a length of 3 3 time cycles. Okay, so C is what is C? C is dash dot dash dot. Okay, so I want a dash, so 1/3 here, 2/3 here, dot. Well, first I got a space of a dot, so that's just 1 and 0. I want a dot, so a single 1 out, so that's a 1 and 0 here. I need a space length of a dot, so 1 and 0 as well. Now I need so we did dash dot, need a dash, so that's 1/3 here and 2/3 there, and then space length of the dot, so this will be a 1 and a 0, and then we have a dash, so that's 1/3, 2/3. Great, that's C. And we do the same thing for I. I is 2 dots, so 1 0 1 0 1 0. That one's pretty straightforward. So on the final last year, this was easy because you could actually figure out whether it's dash and dots just by what I put here, right? So you can do the rest of these. Let's do O. O is dash dash dash. I happen to remember that. So 1/3, 2/3, 1 0, 1/3, 2/3, 1 0, 1/3, 2/3. So you can see how we can quickly construct a parsimonious Markov model to represent each of these letters. The question is, would it actually work for decoding them? So let's talk about that for a second. Go back up to the international for a second. Hold on. Do I have examples down here? Yeah, I do have examples. So what I had here was actually letters of different lengths. Sorry, I had different letters, and here I have dashes that are much longer than normal 3 dots. And so the question is, what would this be? And so when I come up here, I said basically which of these examples would it be? Let me actually move this, make this bigger. There you guys go. Okay, which of these things would this be? And if I just have this, now clearly it's no longer a dash being 3 dots in length, but I still have just clearly a dot and then a dash. So if I actually run this thing through, I need something that is 1 and 0, that allows a 1 and 0. Well, all these will allow a 1 and 0. Right? But then I need something that allows just 1 dash. Right? Well, clearly A will do that. What else will do it? Well, okay, so this can take out that dot, but now I am having I have something like a dot or a dash here, a space, and then I have a dot, and then I have a space, and then I have a dot or dash again, so it can't be C. For I can do, this will be dot, space, and this thing can't suck up all the dash, right? It can only do it in 1 cycle, and then it's done. So clearly, that second part is too long for the I model. L, well, it can handle the first dot, handle the dash, but then it's got, I get stuck here. And so I can do the same thing with O. It can handle the dot here, it can handle the dash here, but it's got to have something else at the end. So I can quickly go through this and actually see, which of the letters above this would match. Now, something came up in class today. I did something more clever than I thought I did. And that was, we started looking at the international code, and we actually wrote out the models for M, and then we actually tried to say, okay, which does this actually work if I actually get something that's real data coming in? Because of this ambiguity here, you would think that the M could match N just fine. So what we're going to do, I wish I could have my camera on at the same time. I can have this on the screen, but I guess I can just copy this down for y'all to see. Give myself some whiteboard space here. Here we go. Let's see if we can do this well. Maybe. Yeah, there we go. So let's see here. Well, see, you can see the top of this. Let's do our our M. I need 10 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so M is these two filled in, these two filled in, and then nothing else. And this guy, 1, 2, 3, 4, 6, 7, 8, 9, 10. N is, I think it's dash and dot, if I remember correctly. So it's got these guys filled in. Okay. So in other words, the code for this is 0, 1 plus, 0, 1 plus, 0, 0, 0, 0, 0. So that would be the regular expression for it. 0, 1 plus, 0, 1, 0 plus, right? Now the question is, given that, so I can make the equivalent of HMM for that. I'm going to run out of room. How much space can you see? Oh, you can still see the top of this stuff. So let me erase this. Our HMMs for this look like going to be 5 states. Why don't we actually try to match them up here a little bit? So this is the first one. See that? Yes, barely. So this is going to be, we're just going to write as zeros and ones. So this is going to be the 0. And that's going to transition. This guy, he's going to output 1s. And he is going to have a transition. We'll keep this in fractions. 1/2 here, 1/2 here. Here, 1/2, 1/2. Oh, sorry, no, there's a space there, so it's 0 and 1. This guy's outputting a 0. And I'm just using too much space already. Half this, 1 and 0, this, half, a half, and then this is going to be a 0. So that's what that looks like. This guy's HMM is very similar. It's also putting out 0s and 1s. 1, 0, 1, 0. Hold it. No, he's got the 1 is got to have 2 states in it. It has to allow 2 states. That's got to be a half. The 0 is just going to immediately transition. So I don't even have to do the self. You have to do these self loops here. I don't know what I'm doing. This guy is going to be output of 1. But the 0 has to have a lot of self loops because you got to put out 4. So let's see here. I expect 5 states. So 1/5. So this got to be a 5th. It's got to be 4/5. Oh, I messed this one up here. This one has to be expect 4 ones, so 4 zeros here. So I have to do 1/4 and 3/4. Now the question is, if I get an incoming n, there's no reason why an n can't match an m. There is a reason why an m can't match an n, because this model right here can't do that transition. So let's show that quick. So what's the probability that I have a sequence, an observation sequence for m, and it was produced by the model for n? So in other words, given what's the probability I see that sequence given that's a model for n? Well, if I do my Viterbi trellis, right? I can make a state. I have a 5-state model, and I have it for every time step. So I have 10 time steps. Wow. But you know what? I should probably do this over here because we're actually saying what's the probability of n producing this sequence. So let's do that. Let's put it over here. Hopefully you can see it without too much glare. So I have to do my 5 states. I gotta do it for these 10 time frames. I'm already making it too big. Two, three, four, five. 1, 2, 3, 4, 5. I'm at this one now. And I have 4 of these. I'm not perfectly aligned, but at least you get some idea. Okay, now if I'm doing the model for n, I come in here, and I can only transition from this state to state 2. Now at state 2, I can transition, from myself to myself, from state 2 to state 2. I can transition to state 3. So let's see, at the end, I know I need to get to the end by this. So we have to finish up that by then. So let's see here. What's the? Well, we can worry about that in a second. But basically, I am doing this. Well, there's no way I can transition here. So I'm gonna get rid of this one. No way I can transition to stuff. So this one can't be the case. So this can't be the case. So I think that is all the ones I need. Okay, so once I'm in state 3, what can I do? Well, at state 3, I can only go to state 4. Yeah. And at state 4, I can only go to state 5. Great. And at state 5, I can only go to myself or out. So I am going to do this or out. Okay. So now, let's look at our data. Is it possible at all this happens? So each time it's just a single arrow, right? These are all going to be 1s. Every time it is 2 arrows, I got, because of my model, I said it's a half for each of these. Half for each of those. And that's it. Everything else is a transition. Oh, except for the bottom. The bottom, each time I transition, I have a probability of going to myself 4/5, 4/5, 4/5, 4/5, 4/5, 4/5, and a 1/5 at the end. Okay. So What's the probability that this observation sequence was generated by this data? Sorry, this model. This observation sequence made by this model. That's what we're seeing here. What's the probability I got an observation sequence that responds M and was made by model N? Okay, so I can come down here from 0. That's great. Probably a 1, getting a 0 here. Come down here. So I'm getting a 1. I'm getting a 1 here. So yes, this can produce a 1. I get another 1 here. So I have to stay in this state, right? So I am going to get my other marker out here. I say confidently and have no idea where my markers went. Oh, I hate that. Oh, here they are. Okay. Give me a blue one. Okay. So, got a 0 over here. I got a 1. I have to be here. I get another 1. Well, this state can't give a 1, so I got to be here. And let's see, the next one I have a 0. Zero. Okay, so it means this state's a 0. That means I have to transition. So that means I'm here. And then I have 2 1s in a row. So I can transition here. I get a 1. But now I have to transition, and this guy's going to put out a 0. But I can't do that. I have to have a 1. I have no choice. I can't do anything. I can't complete the chain. So the probability of OM given this sequence given this model is 0. Great. Well, that's what we want. Well, now let's do something a little different. Let's go the other way. Let's see what happens when I go from, let's change this to the sequence for N given M. Okay. So now I got to change this down here. These guys, get rid of our sequence states. Okay, so now I have to be able to stay in state 4. So I have to have transitions here, right? And these are halves and halves. I know this is small. Just trust me, it's a half and a half, because that's what our model says. Okay. And now this changes as well, because it's a 4th here and a 3/4. So transitioning to myself is 3/4, 3/4, 3/4, 3/4, 3/4, and 1/4. Okay. So now, suppose I'm running this sequence through this model. So I start with a 0. My probability of getting a 0 is 1. Probability in state's 1. So it's 1 times my probability of transitioning. Actually, we'll do it this way. 1 times my probability of transitioning, which is a 1. Okay, what's the probability of getting a 1 in this state? That's also 1. What's my probability of transitioning? It's 1/2. Either if I'm going here or going here. So the probability of getting a 1 from this state, well, it's 1. What's the probability of getting it from state 3, 0? So I'm obviously still here. So I can only be doing this so far. Let's see. The next thing I get here is a 0. So I can't get a 0 here. I have to transition here. What's the probability of getting a 0 from that? It's a 1, but I have to transition probably, which is a half times 1 times. Okay, I have to transition and getting this. So transition is 1. And what's the probability of getting a 1 from? It's also 1. Now, what's the probability of let's see here. I got 0, 1, 1, 0, 1. Then I'm going to have 5 zeros in a row. So let's see here. Have my first transition here. I stayed here. The transition here to the next one. Okay. 0. That's the 0. This is the transition in the 1. This is the transition in the 1. This is the transition in the 0. Then I have a transition, the last state, and I have a 1 output. And now, for each of these, I have self-transition, 3/4, 3/4, and each of these also has 1s in them, because that's the output. So I do this 5 times. 1, 2, 3, 4, 5. And then eventually I transition out. Okay. So the answer is there is a probability that the model for M created the sequence we're seeing for N. And it is equal to 3 to the 5th. 3 to the 5th. Oh, nope, I have 1 too many. Transition, I got my 0. But then I transition to 3, 4, and then I transition out. So it's only 3 of them. So 3 to the 4th over 2 times 2 times 2, that's 8 times, oh, well, these are just 2s as well. So that's 4, that's equivalent of 2 to the 8th, right? 4 4, so that's 16, 2 to the 6, 2 to the 8th, 2 to the 9th, 2 to the 10th, 2 to the 11th. Is that right? This should be 2 to the 8th, to the 9th, to the 10th, to the 11th. Right? So that's approximately Oh, I missed this 4 here. Shoot, no wonder I'm doing it wrong. Okay, so this is actually the equivalent of 2 to the 10th, 2 to the 11th, 2 to the 12th, 2 to the 13th. Okay, 2 to the 13th. This is about 81, right? 3 times 3 times 3 times 3 is 9 times 9, 81, over 8092, I believe, right? Because 2 to the 10th is 1024, 2 to the 3rd is 8, so 8 times 1024 is 8092. So this is approximately like 1/100th. Okay. Now, that's a little disturbing. It means that I can get through this. Since I've changed it into a 5-state model instead of a 10-state finite automaton, I actually can get through the model. But what the real question is what is the probability of seeing observation sequence N given the model for N? And so what we want to see here is a higher probability, right? So now let's actually, instead of drawing all this out, we can just do the calculation here. So we're looking at this model, this data. So we come in with a probability of 1. We put out with a probability of 1. So this is my coming in. So 1 times the probability of state 1 giving us 0, which is 1. And then then I transition with a probability of 1. And then I get a 1 with a probability of 1. I stay in the same state, so I have to do this loop. So I have a transition probability of a half. And then I produce a 1, which is a probability of 1. And then I transition to this state, which is the transition probability is a half. And I output a 0, which is great, probably a 1, times, let's see here. Now I transition probably a 1, and I output a 1, which is probably a 1. I transition to the next one, which is probably a 1. And now I output a 0, which is probably a 1. Now I transition to myself with probably a 4/5. And I output a 0, which is probably a 1. I transition to myself again, which is 4/5. Output a 1. Transition to myself again, probably a 4/5. With an output of 1, which is probably output of 0, which is probably a 1. Okay, so let's see, right? Transition in here. Output. Transition to myself. Transition to myself. So 4/5, 4/5, 4/5, 4/5, and 1/5 in the out. So I should have 4/4, and then I should have a 1/5 in the out. Okay. Wow, that's a lot of work. So now I end up with basically just 4s on top. This is basically 2 to the 8th over what's on the bottom here. I got a 4 there. So basically a 2 to the 2nd times a 5 to the 5th. Okay, wow. Well, I can reduce that to 2 to the 6th over 5 to the 5th. God, so what's 5 to the 5th? Like I said, 2 to the 6th is going to be what, 128? 5 to the 5th. That's 125, which is 3 to the 5th, times 25, which is 5 to the 2nd power. 25, 2, 12, 1, 6, 0, 10, 1, 4, 5, 2. Is that right? No. 2. Is this right? 5, 2, 10, 12, 1, 5, 6, 0, 10, 1, 5, 2. Though ends up being 3, 1, 3, 1, 2, 5. Okay, 3, 1, 2, 5. Well, that's approximately 1/30th. It's actually more than that. And so we see that, well, that's good news, right? That means if I actually compare the probability of model N producing the output of a sequence that belongs to N, 30th, versus the probability of the output of N given the model M, which is about 100th. And so we choose this guy as the winner. So it's not like the difference between, this one's 0 and this one's high, but it is the difference between a factor of 3 or 4 different. So clearly, we have just shown a procedure by which we can go from these, we can go from these things. We can go from this 10, this Morse code. We can actually create a system that actually has the right probabilities to it. It has the right models to it. We can actually reduce those models down to something that's compact, and then when we actually get data coming in, it actually works the right way. So you can actually make a system for Morse code this way. In fact, you could actually have something that just automatically discovers the given lots of examples of A, lots of examples of B, can automatically discover how many states to use, because all it's doing is looking to see these emission probabilities and combining two states where the emissions are the same or very close to each other. And so you have an automatic process by which you can actually create the models for Morse code, and you can actually code this up. You can actually code this from scratch. You could actually create these models automatically. Now, what's excellent here is that we can actually go further with this. If I just had lots of strings of Morse code, international Morse code, I could actually sample it and discover dots and dashes, discover the fact that they're letters, and discover the fact that they're words. And this is a sort of a preview of the most simple way of how we're actually looking at dolphin communication. Can we actually find these pieces and actually put them together into a higher level language? And the answer so far is no, but you have a little hint at the methods that we're using. Okay, now unfortunately I need to run away because I have a PhD proposal I'm supposed to be at. Unfortunately, I can't spend much time on it, but hopefully I can talk to you guys next week. All right, talk to you later.